Hi everyone, move the camera real quick. Maybe this is a better lighting. Okay, so today's lecture is going to be on Thomson 4.7. I'm going to maximize so you can all see it easily. Okay, and it's going to be on, this whole section is going to be a discussion on antiparticles, right? The stuff we've been kind of waiting for when we first start seeing this, when we first derive the Dirac equation, and it turns out the solution turns out to be these 4 component spinors, and I keep telling you, oh, the bottom 2, those are the antiparticles, right? So hopefully we can have a good discussion on why that's the case in this section. Okay, but before we talk about that, let's talk about what happened when we did the Klein-Gordon equation. Remember that? Where we ended up with a bunch of negative energy solutions, right? Well, half of them. Because by applying the Einstein energy momentum relation, right, we can see that the solution to the Klein-Gordon equation is actually either positive energy, well, positive square root of p squared plus m squared, or negative square root of p squared plus m squared. Okay, and at the time we thought, oh, this isn't a big problem, right? Because there is kind of a argument that, oh, maybe this is, could be a physical thing that we can account for. Okay, and this is where Dirac tried to initially show that, well, maybe these negative energy is a physical thing after all. And the interpretation is this Dirac C interpretation, where let's say if we define, some ground state to be for the universe, there's just nothing, just vacuum. Okay, let's call that energy equal to 0. Okay, and what happened is that, right, these negative energy, okay, oops, why does it go blank like that? That's no why, right? These negative energy solutions, or actually negative energy state that are possible, okay, right? So it's possible to have these negative energy, it's possible to have positive energy, okay? But what happened is that the Dirac C interpretation is to think about these as already occupied state, okay? Okay, let's say you just have a bunch of electrons, okay, and these works with fermion mostly, or spin 1/2 particles, and it doesn't actually work with bosons. Okay, since these states are occupied, if you have another electron, let's say, let's see all these, pretend all these are just electrons. Think about them as electrons for now. Right, you have another electron sitting up here. There's no space for it to occupy the negative energy state, therefore it occupies actually the positive energy state, right? And that kind of makes sense, right? So you just have a sea of negative energy that's all filled up, okay? Another kind of neat thing about this is that, let's say a photon comes and excites this negative energy electron, okay? Give it some boost of energy and it excites it, okay? It's now you have a negative energy electron, a positive energy up here with a negative charge. In this spot here, right, where there used to be a negative charge, and those of you who remember your electrostatics, right, the lack of a negative charge is essentially a positive charge, right? So not only when you have this photon come in, excite, creates an electron, it also creates a positive version of an electron, or a positron, right? So therefore, right, this allows you to also see how this pair creation of electron-positron happens. So, I mean, this is a great interpretation, right? So what's the problem with this? Okay, so the energy, right, is a function of momentum and mass, okay, fine. But momentum can be from 0 to infinity. There's no limit of how high you can make this momentum, right? So therefore, this well, right, kind of goes on to negative infinity energy, okay? And negative infinity energy is hard to deal with because it's not a well-defined thing, right? So you imagine that, oh, it takes infinite number of electrons with negative infinite amount of energy in them each to fill the infinite void, to fill the entire universe, just to have a vacuum, right? So you're basically taking infinity to infinity in order amount of energy in order to fill this vacuum of to get you to the ground state where energy is actually zero and you have no electron, no positrons around. And it's only the excitement of these photons that creates them, right? So that's troubling when you have a negative to the negative, so negative infinity to the negative infinity power of energy in order to just even construct your universe, okay? Another problem is that this kind of works for fermions, okay? But what about bosons? Okay, so let's say you have some spin 1 particles, so maybe the Z boson, right? That could have a negative energy state, right? These Z bosons, right? But unlike fermions, okay, right, they don't obey the Fermi exclusion principle. You can have as many bosons as you want in one state as much as you want. So once again, there's yet another factor. So now you have infinity to the infinity to the infinity number of boson in each infinite number of states with possibly infinite amount of negative energy. So that's going to be is a hard to deal with physical interpretation. Okay, so what's the solution to this? Okay, we kind of actually already see this, but what we're going to do is we're going to formalize this in this Feynman-Stuckelberg interpretation, where let's just start with the simplest case where, you know, if we have a particle at rest in the Dirac, the solution to the Dirac equation, right? Where it's some, you know, wave function and it's has some spinner part where it depends on the energy and momentum, but the momentum is 0. And then there's this wavy part where it's usually it's just e to the I p dot x, right, minus et, right? But then the momentum is 0, so therefore you just have minus I et there. Okay, remember there's two parts to this, okay, right? And one thing we learned in maybe back in algebra, right? If you have a negative number, right, and that negative number is the product of two numbers, right? Either b is negative or c is negative. Okay, right? You can make a negative number two different ways. So instead of thinking about the energy as being negative here, what we can do is actually think of the time as being negative. Okay, so what we want to think about is that, well, instead of thinking about this as being negative energy solution propagating forward in time, where time is just the normal time, you can actually think of the solution as positive energy solution, but you have to flip the sign on the time. Okay, it's as if they're propagating backward in time. Okay, and this is what we're going to do as double sign flip, where instead of this e to the minus I et, okay, we're going to think about this as e to the minus I, that's still the same, and we're going to flip the sign on the energy, but then at the same time we're going to flip the sign on the time also, and therefore it's actually the same function, right? The function didn't change because we have to put in two negative signs. Okay, so remember that for the antiparticle solution, right, the energy of the particle in the Dirac equation is negative m, but now if we transfer this to be negative e, right, we actually get negative of the negative m, and therefore you actually get positive m, right? So in this energy, in this negative flipping the sign of the energy, yeah, you actually get a positive rest. Well, it's equal to the positive rest mass in the case that the particle is actually at rest. But, right, we have to flip the sign of the time, okay? And that may be like, okay, that's a little wonky, but surprise, surprise, you actually have done this already in chapter 1 when we start drawing Feynman diagrams, okay? Let's do the example where we have maybe an electron and a positron, right? One particle, one antiparticle, annihilate into each other, right? And they produce, you know, either a Z or a gamma, and produce something else. It doesn't actually matter what that is. Remember, the way we draw this is that the electron is drawn as being propagating forward in time, okay? The positron is drawn as propagating backward in time already, right? So this is an antiparticle, right, propagating backward in time, okay? So it actually comes in very natural in the Feynman diagrams where you have particleness, right, coming into a vertex. Whatever particleness come into the vertex, that particleness has to leave the vertex, okay? and therefore these arrows are drawn, right, to follow the particleness of flow from 0 to some positive time. So therefore, any antiparticle is drawn as a particle going backward in time. Okay. So what happens? What happens when you do this? Okay, because you can't just change the sign on time. Okay. Well, the energy solution, right, becomes the negative of this energy. So what used to be negative m becomes positive m, which is what we want. But there's a consequence to this, right? Momentum's also flip-flying, right? If you have a particle going forward in time, right? If you're reversing time, it's actually going in the opposite direction. Okay. So to keep track of this, what we're going to do is we're going to define yet a new set of solution to the to the four component wave function to this the solution to the Dirac equation. Okay, we're going to take U4. Okay, let's look at the right hand side first. Okay, we're going to take U4. Right, remember we have to flip the sign of the energy. Okay, this used to be, if this was at rest, this used to be negative m, right? But by flipping the sign, right now this becomes positive m, right? Negative times a negative. Okay, right. And if we flip the sign, if we make the time go backward, this also makes the momentum in the opposite direction now. Okay. In effect, right, so normally, let's write the U1. Okay. Sorry, not the U1s. Let's write sine 1. There's some normalization 1, and then U1, right? E, you have some momentum, e to the I px, right, times e times t, right? That's the normal one. Okay, but since we're going to flip the sign of energy, right, this becomes negative of that. Right, we have this negative energy inserted in there, but instead of positive momentum, we insert a negative momentum in there. Okay, we can factor out both of these negative ones, right, negative ones. Okay, and this basically becomes U4 negative E negative P, right? E is factoring out that negative one, just put it in front, right? You still have this P dot X, okay, minus. Right, there's two minus sign here. I'm going to remove one of them, okay, or factor out one of them. I'm going to define this, right? This looks almost the same, right, except for this negative sign in front, okay. And this U spinner, right, we're going to both the momentum and the energy value got flipped. So we're going to define, instead of calling this U4, we're going to call this V now, with the energy and the momentum flipped. Okay, there's a bunch of double flips happening. Sorry about that, but that does make it so that eventually when we write the full solution, it makes it really easy to interpret. And therefore, these V's are always going to represent antiparticles, okay, as opposed to particles. Okay, and similarly, V2, right, is the same flip. But instead of flipping U4, we're going to flip U3 instead. Okay. So applying this math, right, just as what we did in Thomson, but now we're thinking about them as antiparticles, where we flip the sign of time. Okay. What we need to do is then, well, instead of having a solution of the E being a negative side, instead of having the solution being negative m, we're going to flip the sign twice. So we put a negative sign on this side, which puts in an additional negative sign on this side. Right now, instead of a negative m, here we're going to have a positive m. Okay, and since we're defining this v function as being negative e, right, so whatever negative e is, it transformed to just a regular e. I know it's very confusing, but right, in this definition, E is going to be equal to M. Okay, so therefore, right, the full written out spinners with a free Dirac particle is going to be written as V1 equals to some normalization factor as usual. Okay, the momentum, right, Px minus I Py, right, divided by E, but instead of minus M, okay, as in the U4 case, let me just show you that, just make sure that we know that what we're talking about. Okay, if we go back to the previous section, right, these are the free particle solutions, right? Okay, notice that there's this negative m's here, right? Okay, what's gonna happen is that negative m represents the negative energy of the antiparticle. So we're gonna flip that sign because we basically forcibly force the energy solution to be positive. Okay, so this is also positive m here. Okay, so that's V1 and V2. Okay, all right, sorry, that's V1, and V2 is very similar, but then you just switch the place of PZ and PX and PY. Okay, with a little bit of negative sign in front of the PY. Okay, so these represents, you know, antiparticle solutions. Okay, or well, these represent positive energy solutions, right? But going backward in time. Okay. Down here, V3 and V4, right? Just as will happen when we just did this in the particle case, these will actually turn into negative energy solution, right? You notice these negative m's here, right? Okay. These are negative energy solution, but still going backward in time. Okay. We're not going to use this, so don't worry about it, because we actually have a complete solution, okay, without them. Okay, what we're going to do now is that, well, these are the solution we want, right, with positive energy, and we also have positive energy solution from the particle side. Let me go back to the previous section, right, where we have the positive energy solution down here also, right, with U1 and U2, and since we made V1 with U4 and V2 with U3, right? Remember, these are orthogonal independent solutions, right? As long as we make the V1 using U4 and then V2 using U3, right? We still have all the possible solutions to the Dirac equation if we define V1 as, you know, in terms of U4, and then V2 in terms of U3, okay, by just flipping the sign of the energy and time. Okay, so what we're going to do is in the Feynman-Stuckelberg interpretation, we're going to pick out only the positive energy solutions, okay, where the particles, right, is going to be represented by U1 and U2. Okay, these are all the particles, right? Right, and then this is the spin up, this is the spin down, and then the V's represents the antiparticles. Okay, this is spin up, this is spin down. Okay, and as usual, the normalization factor is found by just calculating the psi dagger psi and we're going to see that with these normalization here, we're going to see that all these normalization factor will actually come out to be square root of E plus M. So I have you guys check that in your homework. Okay. So with this, okay, I know this is slightly long. Okay. What's going to happen is that we also have another correction we need to make, and these are the operators on antiparticles. Okay, because the particles, the operators we're used to using, right, expect times to go forward, right? All these antiparticle states have time going backwards, so we have to actually make sure to flip those properly also. Okay, the first thing to do is the Hamiltonian. Okay, go white. Okay, so normally the Hamiltonian, right, is just the Hamiltonian acting on some state, give you the I partial by partial t of that particular state, right? Tells you how that moves around. What we need to do is actually define a antiparticle Hamiltonian operator, right, where we always gonna flip the sign whenever we see time, energy, or momentum. Okay, so therefore, right, the antiparticle version of the Hamiltonian is going to have this negative I in front as opposed to a positive. Okay. Similarly, for momentum, the momentum operator for regular for particles, right, is negative I, the gradient, where this gradient is partial part partial x, partial y, partial y, and so on like that. So we'll have to write that out. Okay. Instead of negative I, we're going to make that a positive I, right? Because we have the particles, whatever particles was going forward in time, right, it's going to go in the exact opposite direction when we flip time backward. Okay. Since momentum flip, okay, rotational angular momentum also flip sign. Okay. Okay. Why don't the spatial position flip, right? We only flip time. So space, x, y, z is still the same, and therefore you only pick up one factor of negative sign here in the angular momentum calculation. So therefore, angular momentum also flips to this negative angular momentum. Okay. Okay. Similarly, with spin is also going to be negative. It's a little bit harder to picture because spin is the intrinsic properties of particles as opposed to having a physical. You can't physically picture them in classical mechanics, right? But we do also have to flip the sign of the spin operator for antiparticles. Okay, so this forces us to have some spin up and spin down particles, just as what we expect for the spin 1/2 particles. Okay, so that's how we deal with this one sign flip, right? Okay, what we're going to do now is I'm going to go through a little bit of this charge conjugation symmetry, just to, because this is actually a good place to talk about it, but I'm not going to require you to do any homework. We just want to introduce you to the idea initially. Okay, so previously, right, we have this operation, this thing we just did, where we made all the negative energy into positive energy. Okay, and the way we did that is by basically reversing time. So this is a time reversal operation. Okay, when we did the time reversal operation, what happened is that we made all the particles, the math of all the particles behave as if they're antiparticles, and all the math from the antiparticle behave as if they are particles. Okay, and this brings up another operation that's sort of interesting. It's known as the charge conjugation operator, or not operator, charge conjugation transformation. Okay, because this is essentially what we did, right? We previously, but what you can do is you can also just do it arbitrarily, because the universe actually doesn't care whether or not something is particle or antiparticle, as long as all the stuff in the universe are particles, right? They'll behave the same way. So an electron is a particle, a proton is a particle, right? A neutron is a particle, right? And these make nucleus, and then you can make atoms out of them. But if you have positrons, the antiparticle universe, right, then you have an antiproton and an anti-neutron. These will also form atoms, and you can make a whole universe out of that. So it just happens that we live, well, it just happens that we live in our universe, therefore we define our universe to be the particle universe. But what you can do is actually do this thing called a charge conjugation, where we basically flip the sign of all the charges in the universe. So in this case, right, we flip electrons to positron, and then proton, regular positive charge proton to negatively charged proton, or the antiproton. So you can do the same thing here. This transformation is known as charge conjugation, and it's usually done with this, capital C operation. Okay, what this does is basically just transform whatever particle state you have into its antiparticle state. So it changes U to V's. Okay, what it also does is that it also put this additional negative sign in front. Okay, remember the wave part of these solutions, right? Let me go back up to, is it all the way up here? I just talked a lot already, right? right? When we did this, right, we pull out an additional negative sign because of that, okay? So that also happens, okay? So this is symbolized by some symbol C, known as the charge symmetry, and the charge conjugation is a symmetry in electromagnetic interaction and also the strong interaction, but the weak interaction actually breaks this, and I think it actually breaks this 100% of the time. So we're going to talk about this when we get to the weak interaction, where we have to deal with left-handed and right-handed particles, which is actually going to be the next section in this chapter, but we don't have enough time this week to cover it, so we will do that beginning of next module, in module 6, okay?